Hi, welcome to my topic Circuits and Networks. I am Ravikant Mallajushla and today we are going to discuss with mesh analysis and node analysis, especially with the problems involved with dependent sources. Now you can see here you have in figure 1 you have a dependent source, that is current dependent current source 2I1. This current is traveling in 5 ohms in this direction. So we need to find out what voltage developed across 10 ohms, that is this branch voltage we need to find out, and we need to find out the value of current which is traveling in 15 ohms in this direction. So this we can do with the help of mesh analysis and node analysis. So method 1, I'm taking the mesh analysis. While taking the mesh analysis, I have to take the direction of the loop currents. So I'm taking the direction of the loop currents in clockwise direction. So you can see I1, I2, I3, all three currents are taken in clockwise direction. And I'm applying KVL to loop 1. When you're going to apply KVL to loop 1, it states that Kirchhoff's voltage law, that is algebraic sum of the voltages in a closed circuit is equal to 0. So 5 I1 10 I1 minus I3 plus 25 should be equivalent to 0. So this is what we have framed the equation. With this you can rearrange the values and this equation is framed as 1. After getting the equation 1, I am concentrating on loop 2. Fortunately, 2I1 is a dependent current source whose direction is acting quite opposite to the loop current I2. So that is why here I2 is equal to minus 2I1. When you look at this loop 3, I3 and the direction of the current source are one and the same. So I3 is equal to 3.5 amperes. With these three equations, we can get the values of I1, I2 and I3. So substituting 3 in 1, I'm going to get the value of I1 which is 0.6667 amperes. Remember this equation, we have to cross check this value with method 2, that is applying node analysis. Let us go with the next substitution. Substituting equation 4 in equation 2 will give you the value of current I2. So I2 here obtained as minus 1.334 amperes. Now you can see from equation 4, 5 and 3 we got 3 loop currents as I1, I2 and I3. Once we obtain the values of the currents, let us concentrate on the voltage, which is our basic requirement. We need to find out the voltage across 10 ohms. So it will be the current which is traveling in 10 ohms, that is I1 minus I3. So the value of current is obtained as minus 2.83 amperes. Therefore the voltage across 10 ohms according to Ohm's law is 10 I1 minus I3, which will get the value as minus 28.3 volts. Now we have satisfied with the first solution. Let's go with the second solution. We need to find out the current in 15 ohms and it was shown in this direction. So the value of current through 15 ohms is nothing but I3 minus I2, which will be equivalent to 4.8334 amperes. Now this is the answer what we have to remember in finding out the current through 15 ohms. Now once we obtain these two currents, let us cross check with method 2, that is applying node analysis. So the question is reframed as find the current through 5 ohms here and 15 ohms here for the circuit shown in figure 1. So for the same problem, we are finding out the currents I1 and I. So method 2, assuming the node points to be at higher potential. So all the node points are assumed to be at higher potential, V1, V2, V3. I have selected in this direction. And whenever I'm going to take the node voltages as V1, V2, V3, I'm assuming as higher potential voltages. And I'm going to deal with individual nodes by applying KCL. So what are the requirements? We require to get the value of current I, which is flowing in 15 ohms. That is nothing but according to Ohm's law, V equal to IR. Therefore, I is equal to V by R. So V is nothing but the difference of the voltages which is flowing in this 15 ohms. So I is equal to V3 minus V2 by 15. This is one requirement. Another requirement is I1. I1 it is acting quite opposite to the assumed potential because assumed potential is higher potential and the direction of the current is in this direction. That is why I1 is equal to minus V1 by 5. If the direction of the current was in this direction, then it will be positive V1 by 5. So these are the two currents we need to find out. So I'm going to apply KCL to all the nodes. Before that, please observe carefully. Here you have node voltage V2, which is given as 25 volts. It is direct value, so V2 is equal to 25 volts. Now I1, it is a requirement. I1 is minus V1 by 5, that is this branch current, and you have I, which is traveling from V3 towards V2, that is V3 minus V2 by 15. These are the things which we have derived from the given problem. So applying KCL to the node 1 will give you the value as V1 minus V2 by 10. This is one branch current. Then you have V1 by 5. This is another branch current. This is positive because we are assuming V1 to be at higher potential. And current is leaving this particular node. So that is why it is positive 3.5 amperes, which is equal to 0. This will give you the value as V1 equal to minus 3.33 volts. Here we have substituted the value of V2 over here. That's why we got the value of V1 to be as minus 3.33 volts. Once we obtain the value of V1, we'll apply KCL to node 3. When you're going to apply KCL to the node 3, we're going to get V3 minus V2 by 15 as this branch current. Then you have minus 2I1, which is coming towards the node V3. So that is why it is minus symbol. And similarly with the case 3.5 amperes, it is coming towards the node V3. That is why minus 3.5. It is equal to 0. With this, I'm going to get the value of V3 to be 97.4805 volts. Now this is the value of voltage V3. Once we are obtaining the node voltages V1, this value, V2, the given value, V3, we can obtain the value of branch current I, which is nothing but V3 minus V2 by 15. So we are substituting the values of V3 and V2, and I'm going to get the value as current 4.832. If at all you observe keenly, we have obtained the same result when we have applied the mesh analysis. Similarly, we are going to apply the value of V1 to obtain the value of current I1, which is 0.664 amperes. Now this is quite similar to the current which we have obtained in method 1 as equation 4. Please cross check and satisfy your results. Now this is how we apply mesh analysis and node analysis for the dependent source problem. This is an example 1. Let us go with an example 2. Now you can see in this figure 2, there are the different sources which are given. That is, one is the active voltage source, then you have the rest of the sources as dependent sources. Here you can see 2IY, it is a current dependent current source, 4IX current dependent voltage source, 2IX again current dependent voltage source, 10IY again a current dependent current, and it's a voltage source, so it will be called as current dependent voltage source. So we need to find out the value of Ix and Iy. These are the branch currents here. So method 1, we are going to apply KVL by assuming all the loop currents to be in clockwise direction. So current I1, I2, I3 are selected. Now once these currents are selected, I'm going to identify the branch currents which are required. Ix, according to the mesh analysis, will be equivalent to I1 minus I2. Okay, then Iy will be equal to I2. Here it is a branch current Iy, and I2 is the loop current. Both are acting in the same direction, so Iy is equal to I2. And I3, you can see the current loop current direction I3, which is quite equivalent to the dependent current source, that is 2Iy, and Iy is nothing but I2. So these are the things which you have to identify from the given problem. Once we obtain the branch currents, then we can easily obtain the total loop currents, and then finally we can obtain the requirement of the branch current, that is Ix and Iy. Now the things which we have already determined from the given problem, then applying KVL to loop 1 will give you minus 5 volts plus 5 I1 minus I3 plus 2 Ix, the given current dependent voltage source as it is taken, plus 2 this branch voltage, that is 2 I1 minus I2 plus 10 Iy equal to 0. Now this is the equation we have framed using Kirchhoff's voltage law. Then we are going to obtain the value for all these things by substituting equation 1, 2 and 3 in equation 4. Like this we have substituted the values, and we have framed 9I1 minus 4I2 is equal to 5, and this is equation 5. This is one equation of the mesh analysis. Now once we obtain the equation 1 for the mesh analysis, that is loop current 1, then we are going to concentrate on loop current 2. So applying KVL to loop 2, and minus 10y, this is the one voltage drop over here, then plus 2 I2 minus I1 plus 2 I2 minus I3 plus 4 Ix plus 2 I2 equal to 0. This is equation 6, and we have to again substitute the values of 3, 2, 1 in this loop 2 equation. Then we are going to get the equation as 6I2 is equal to I1. Now this I'm taking as equation 7. Now already we have obtained equation 5 and equation 7. So substituting equation 7 in equation 5 will give you the value as I2 is equal to 0.1 amperes. 0.1 amperes is the value of I2. Once we obtain the value of I2, we can obtain the value of I1, which is 0.6 amperes. So this I'm treating the current equation as 9. So I1 we obtained, I2 we obtained, and what are the requirements? Our requirements are branch currents Ix and Iy. So Ix already is we have determined as I1 minus I2, substituting the values of I1 and I2 over here, which is going to give you the value of Ix to be 0.5 amperes. Now this is the required branch current in this particular branch, and then Iy, which is nothing but equivalent to I2, and this is obtained as 0.1 ampere. So these two results we have obtained using mesh analysis. Whether we have done the right approach or wrong, we can check it out with another method, that is method 2, that is node analysis. So I'm going to go for the node analysis. So I'm simply identifying the node points V1, V2, V3 to be at higher potential. Lower potential is 0 volts. Once we have identified this, try to identify the branch current requirements. Ix, you see this Ix, it is flowing over here. So it will be V2 minus 10 Iy by 2. The difference of the voltages divided by the resistance will give you the value of branch current Ix. Iy, it is V3 by 2, V3 by 2. So Ix, Iy, these are the requirements, and I'm substituting Iy in Ix. So I'm going to get the value of Ix as V2 minus 5V3 by 2. So this we have obtained already, and then I'm obtaining Iy as V3 by 2. These two equations are obtained in the Roman letter forms. Now V1 is equal to 5 volts. You can see the node voltage over V1, the given active source, it is between positive V1 and negative is assigned to 0. So this entire branch voltage is nothing but V1, which is equal to 5 volts. Once we obtain these values of Ix, Iy and V1, we have to frame the equations using node analysis. So applying KCL to node 2, because V1 is already obtained now. So that is why we are going to node analysis with 2. So you can see V2 minus V1 plus 2Ix by 5. This is one branch current. Then you have V2 minus 10Iy whole divided by 2. This is another branch current over this. Then you have V2 minus V3 minus 4Ix divided by 2. You can see minus sign is assigned towards 3 and plus towards 2. That's why I have taken minus 4Ix, because V2 is assumed to be at higher potential and the rest of the voltages we are treating as to be at least potentials. That's why we are taking the minus symbols. Okay. In the first case, you can see plus sign is towards V1 and minus is towards V2, and that is why we are taken V2 minus V1 plus 2x. So that is the main difference you need to observe in this particular node equation. Now substituting the values of Ix, Iy from Roman letters 1, 2, 3 in the given equation. Please observe carefully how the equation is framed. Ix is substituted here, Iy is substituted here, again Ix is repeated here. So we have substituted all these values and we have recreated our node equation 2. Fortunately, we got the values to be 2v2 by 5 plus v3 is equal to 1. Simplification will give you an equation 4. Now the same thing we are going to apply with node 3. Node 3 we can apply. Before that, we need to remember what we have obtained already. Ix and Iy we have already framed as a branch currents, and we need to substitute in these two currents in node 3 equation. So applying KCL at node 3, you can see there are three branch currents which are connected to node 3. So V3 minus V2 plus 4Ix is by 2 plus V3 by 2, and this current source, dependent current source, is traveling towards node 3. That is why it is minus 2Iy is equal to 0. Now substituting the values of 1 and 2 in this equation. So I am going to obtain V2, which is equal to 10 V3. So this I am treating as another equation, equation 5. Substituting equation 5 in equation 4, we're going to get the value of V2, which is 2 volts, and V3 equal to 0.2 volts. Once we obtain V2 value and V3 value, we can get the value of Ix, which is our basic requirement, which is nothing but 2 minus 5 into 0.2 divided by 2, which will be giving you the value of the current as 0.5 amperes, and Iy is equal to V3 by 2, that is 0.2 by 2, 0.1 amperes. So this is how we have obtained the values of Ix and Iy using node analysis. Now you please cross check the results with mesh analysis as well as node analysis. We got the same results, and this is how you come to a conclusion that whatever the method you employ, you have to get the same magnitude of the currents in the given problem. So today we have done with mesh analysis and node analysis, especially with the dependent sources. If you please like my video, share among your friends, like it, subscribe it, and press the bell icon for the future notifications. Thank you.